Graphing proportional relationships. Last class, we determined if X and Y had proportional relationship or had direct variation from a table or ordered pairs. Now we're going to take a look at graphs. We're still going to have the information in a table on some of these, but we're going to graph them and then determine if we can find a similarity between the graphs of those that do have a proportional relationship. So if we take a look at the first example, Olivia sold water bottles over 4 days. Create a graph to determine if the quantities of bottles and number of days are proportional. If the quantities are proportional, what is the constant of proportionality? So I'm going to give some labels to my axes here. I'm going to say number of bottles here and number of days. Okay, if we're taking a look at the table, it goes 1, 2, 3, 4. So I'm going to go ahead and I want to spread it out a little bit. So I'm going to put 1, 2, 3, and 4. And then my other inputs are 4, 8, 12, and 16. 4, 5, 6, 7, 8. That only goes to 12. So I'm going to make it by 2s. So 2, 4, 6, 8, 10. There's 2. 12, 14, 16, 18, and 20 will be right here. I didn't give myself a lot of room, did I? Okay, so if we plot those points, 1, 4 would be here. 2, 8 would be there. 3, 12, 3, 10, 12. And then 4, 16 would be 10, 12, 14, 16. Okay, once you graph your points, you're going to want to connect them. You can use a ruler if you have one, or a straight edge of some kind. That kind of usually improves your line drawing. I'm going to use a ruler because my line drawing is pretty awful. Okay, how about there? Okay, there we go. All right. It asks that they're proportional. I'm going to wait a second. I want to actually graph both of these, and then I'm going to do the proportionality. Mix it up a little bit. Okay, so the second one is number of boxes and number of pencils. I'm going to put boxes here and pencils here. And it's 2, 4, 6, 8. So that's 8. And then this is also going by 16, so I'm going to do it by 2s again. 10, 12, 14, 16, 18, and there's 20. Okay, so 2, 4 here, 4, 8, 6, 12, 8, 16. And I have these notes available for you to actually make a copy of on your iPad, or you can print them off if you want to add them to your paper notes. If you have paper notes, if you have iPad, you're fine. If you're doing all your notes on your iPad. Okay, I'm going to provide a blank version, and a completed version will be in your Google Classroom. That's kind of good. It's a little bit. Let me move it up a little. A smidgens. Come on, little ruler. There you go, buddy. It helps to talk to the ruler. Sometimes that makes it cooperate a little better. Oh, I should have erased that of the line first. Oh well. Boop. I'll kind of, there we go. Clean it up a little bit. So it looks like that. Now I'm going to actually calculate to see if the quantities are proportional. Because it's asking me to find a constant of proportionality, I might as well just do it in that manner. Because the constant proportionality is y over x, I might as well just do y over x, right? My x-axis was days and my y was bottles. Okay, and then here, x, y. Now, some of you may be like, well, how did you know what label to put on what axes? Normally, I think about what the rate would be because proportionality has a lot to do with unit rate, right? The constant of proportionality is basically unit rate. I think about what makes more sense. Number of bottles per day makes more sense than days per bottle, and number of pencils per box makes more sense than number of boxes per pencils. So I determined it that way. I think it's a pretty good rule of thumb. So if I take y over x on all of these, that's 4 over 1, 8 over 2, 12 over 3, and 16 over 4. If you notice, these are all equal because they all equal 4. Okay? And my constant of proportionality is 4. Boop. Now, I'm going to do this one. 4 over 2, 8 over 4, 12 over 6, 16 over 8. These all are equal because they're all equal to 2. And that is our constant of proportionality as well. Okay, is there anything that you notice about these two graphs? They both have a positive, what we would call positive slope. We're going to get to slope eventually. But basically, it's going up from left to right. Okay? Obviously, these are starting off at 0, 0. If you take a look at the line, it goes through 0, 0. This one is a little crooked. So it really does go through 0, 0. You may notice that. They're pretty evenly spaced out. Your points don't have to be evenly spaced out. They just all need to obviously be on the line for you to determine if they're proportional. I'm not going to say everything about this, but you may have noticed that there are some things that happened here with these two tables that had proportional variables that had a proportional relationship. Okay, one, the lines were straight lines. Now, lines technically are supposed to be straight, but you're going to come up with some graphs that are not straight once you hit high school, like some hyperbolas and some parabolas. We're not going to do that this year. So you want your line to be straight, and the line has to pass through the origin. Okay? Is the line slanted? What it means by slanted, because I think that's a little misleading, is it can't be vertical or horizontal. Okay? Meaning horizontal or vertical, straight up and down or left to right, parallel to the x-axis or parallel to the y-axis, basically. And they weren't, so it is slanted. Yes, our lines were slanted. So if the answer is yes to all three questions, the graph is a direct proportion. Okay? If it's not, if any of them is no, if any single one of those answers to the questions is no, then it is not a direct proportion. Doesn't matter if two are yes and one is no, if all it takes is one no for it not to be a direct proportion. So now we're going to tell whether each graph represented a direct proportion. If so, find the constant of proportionality, then write a direct proportion equation. So we're going to do a few examples to kind of hit home what we just went over on the last slide. So is this a direct proportion? Why or why not? Well, there were a couple of things that we saw on the last slide that determine that. Is it a straight line? Yes. Does it go through the origin? Yes. Is it slanted? Yes. So yes. Yes. Okay. It is a straight line. I should almost put straight here. I'll erase this and put straight slanted line. Straight slanted line that goes through the origin. Okay? Choose 3 points on the line and write as ordered pairs. Okie dokie. I'm going to do the ones that are like really easy to see. These 3 right here, because they go right on the intersection of 2 lines, okay? So we have, you remember your x first and then your y. So that first point that I drew on right here is 110. The second point is 220, and the third point is 330. Okay, x, y, then first. X first, then y is what I meant to say. So if so, the constant proportionality is, let's determine. So if this is x and this is y, and we know that it's proportional, we can just take one of them, right? And so our constant of proportionality is 10, and you just plop that into the equation, right? You just plop it, boop, in there. And your direct proportion equation is y equals 10x. Next. Okay, we're doing the same thing here. Why or why not? No. Can you figure out why? Actually, can you figure out why not? It's a straight line, slanted, but it doesn't go through the origin. So does not go through the origin. Wah, wah. Okay. We actually don't need to do these other ones because if it doesn't have direct proportion, then it doesn't have a constant of proportionality or a direct proportion equation. So those are NA. Boop. It's actually easier if they're not, right? Okay, remember what I said? That's super important algebra, okay? If you have x's and y's, you want to plug them in. Always makes it so much easier. Okay, now you may notice that the table is blank. That's because you can literally put in whatever you want. Whatever I want for x. Okay, x is input, so we can put whatever input we want. If you remember your little function machine from elementary school, right? I'm going to go ahead and put 0 as one of them. And then to keep my y values down, and you may ask, why do you need to keep your y values down? Because I only have so many squares on my grid, and I don't want to go too crazy with it because then my points will go off the grid. So I'm just going to put 1, 2, 3, and 4. Make it easy. Okay, now for your x values, you can literally put anything. But it does need to tie to your y values, and you do that by plugging in. Meaning your y value equals 3 times whatever you put for the x. In this case, it was 0. Okay, 3 times 0 is 0. Okay, y equals 3 times 1 in this one because I have my x value as 1. So that means y would be 3 times 1, which is 3. Okay, and you just fill in that way, just changing your x value depending on what you set it as. So this would be 6, 9, and 12. If you want to, it's up to you. It's not necessary, which is why I only have the table the way it is. But if you would like, you could also have a column for your ordered pairs. That's just if you need the visual of the ordered pair to be able to graph it easier. So you just take your x value and your y value, write them down, 2, 6, 3, 9, and 4, 12. Okay, like I said, not necessary, but it is kind of a nice little visual there to help you with your graphing. I'm going to change the color here so I can actually, let's do labeling my x and y. I'm going to space it out a little bit over here. 1, 2, 3, 4. I didn't label my axes because I didn't have anything to label it with. It didn't come with any labels. It was just talking about x's and y's. So I don't really need to label it, but I am going to put my numbers in. So then on my y, 2, 4, 6, 8, 10, and 12. We almost topped out. Okay, so we've got 0, 0, boom. Actually, I wanted to use a different color. That's what I wanted to use a different color for. 0, 0, 1, 3, 2, 6, 3, 9, and 4, 12. 4, 12. Okay, use my ruler. Honestly, I always have kind of like a little bit of trouble with this. I think just drawing lines in general is a little challenging for me. I don't know why. Okay, that's not too bad, right? It's not horrible. Anyway, as you notice, if I had drawn the line a little better, it goes through the origin, is a straight slanted line, directly proportional. right? If you're wanting to know what our constant of proportionality was, it's right here, okay? Your constant proportionality is always going to be right there, okay? It's the coefficient of x is your constant of proportionality. Goals. Bob's Burger Barn. Let's just change it to Bob's Burgers because it's the best show. There. Has a special deal of 4 hamburgers for $6. I don't think those are high quality burgers if you're getting that many for 6. At this rate, how much should it cost you to buy 3 hamburgers? Fill in the table to show the price of 0 to 5 hamburgers, then graph the information. You should question what's in those hamburgers if they're that cheap. So 4 hamburgers for $6, right? I mean, I think it's pretty safe to say that 2 hamburgers, if you're talking about the same unit rate, 2 hamburgers would cost $3, right? So we're going to have to do unit rate on this. If you're doing 3 divided by 2 or 6 divided by 4, let's do it this way. K equals 3 halves, and 3 halves is 1.5. That means 1 burger would cost $1.50. 0 burgers would cost $0, unless you're getting cheated. 3 hamburgers would just be $1.50 times 3, which is what? $4.50, right? And then this would be $7.50. Cooly cools. I hope you understand what I did with that. What is a unit rate? We determine that is, remember with unit rate to actually label it. $1.50 per burg. $1.50 a burger. That is so cheap. You might be eating some sketchy meat there. Don't eat. Be careful with really cheap burgers. Number of hamburgers, I'm going to space these out a little bit. 1, 2, 3, 4, and 5. And then we need to go to 750. Let's see, 1. Okay. I'm going to do 2, 4, 6, 8. That'll work. Okay. I don't want to go off the chart, and I kind of want to do it in a visually easy way to do it. Okay, so 0, 0 burgers, 1, 150. 1, that'd be 1, and then halfway here. 3 is $2. No, 2 is $3. There we go. Read properly. 3 is 450, so I go halfway between here. 4 is 6, boom, and 5 is 750, so I go to 7 and a half. Handy dandy ruler. Boom. There we go. Look at that. Ain't she a beaut? Boop. That is a mighty fine line. Look at it. I'm just going to stare at it for half an hour. It's so beautiful. Okay, so as you notice, it goes through the origin, right? Straight, slanted line. Huzzah. Beautiful. Okay, do we answer all our questions? At this rate, how much did it cost to buy 3 hamburgers? So 3 hamburgers were $4.50. We filled in the table and we answered the unit rate. We're good. Actually, I lied. So I do want to put even though it didn't ask, the direct proportion equation would be $1.50x. Now notice I took the 0 off just because I made it cleaner. If you put 1.50x, it's the same thing, right? Next, make a table for each line, then find the constant of proportionality, which situation has a greater constant of proportionality. So let's start with line A. Line A, I'm going to look at some points. Boop, boop. Oh, those are the easier lines. Oh, when x is 1, too. Never mind. I'm looking at the wrong one. 2, 4, and 6. 2, 4. Now notice 6 goes off the graph for A. That's okay. We can still calculate it because we know that it has a direct proportion. X and Y have a direct proportion. Okay, so for 0, we obviously have 0. 2, we have 6, and 4, actually 4 goes off the graph too. We only really need 1 point. We know this has a direct proportion, so we can already take this and do y over x. In this case, that is 6 over 2, which, oops, I wrote 3. There we go. 6 over 2, which is 3. My brain was racing ahead. Okay, so that means that you can just do 4 times 3 is 12, 6 times 3 is 18, right? That's how you figure it out. The constant of proportionality is 3. So k equals 3. And if you don't know where I got that from, basically, if y over x is 3, that means x times 3 is y. Okay? Basically, y equals 3x. And you just plugged in for every x to get the missing numbers from the table. Okay? B, we need 2, 4, and 6. B, 2, 4, and 6. So 2 is 1. This one's like easier because everything is on the graph. 4 is 2, and 6 is 3. Okay, obviously this is 0, 0. I don't even need to calculate anything on this, right? But I do know that my constant of proportionality here is 1 over 2, which is a half. I don't need to simplify it. You don't need to turn it into a decimal if you don't want. You can if you want to. I like to leave it as a fraction because that's how I roll. So y equals 1/2 x. Now it asks which situation has a greater constant of proportionality. That would be line A, because the constant of proportionality is 3 for that one, and the constant of proportionality for B is 1/2. Next. Next and last. So the tortoise can walk 1/2 mile in 1/4 of an hour, and the hare can run 1.5 miles in 1/2 an hour. Fancy pants. Complete the table for each animal. Graph each animal's rate in a different color. This is the old tortoise and the hare situation, isn't it? Alrighty. So the tortoise, should I do them? I'll even do them in different colors. The tortoise in 0 hours can run 0 miles. I don't know if you knew that. We're assuming that we're just looking at whole hour situations. And because my graph is already filled out, I'm going to also put 1, 2, and 3 hours in there. If you look at the x-axis down here, 0, 1, 2, 3. Okay? And then my miles. So for 1 hour, it can go 1/2 mile in 1/4 of an hour. Okay? So there's a couple different ways you could do this. You can just calculate it using what you know about fractions, or you can say that this is our hours, so it's x, and this is our y, right? And you can do y over x, which in this situation is 1/2 divided by 1/4. If you recall how to divide fractions, you keep, change, flip, which means that it is 4 over 2, which is 2 hours. Okay? What that means is our constant of proportionality for the unit, or for the tortoise, also it is the unit rate, is 2 miles per hour. Okay? So I'm going to put that to k equals 2. What that means is we can just plug it in. So 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6. Okay? Next, we have the hare. I'm going to use a different color here. And the hare can run 1.5 miles, y, and hours is x. So we're going to do the same thing. 1.5, I'm going to change it to improper fraction though. 1.5 is 3 halves. So 3 halves divided by 1/2. Right? We're going to keep change flip. 3 halves times 2 over 1. Okay, you can either say 6 over 2, or you can cross cancel if you want. And you just know it's 3. So k equals 3. Remember, constant of proportionality is also unit rate. So that means 3 miles per hour. Okay? And if we're filling in, we're going to fill in the same that we did for the tortoise. That would be times 3. So 0 times 3 is 0, 1 times 3 is 3, 2 times 3 is 6, 3 times 3 is 9. Okay? Which animal is faster? The hare. How do I know? Common sense. And math. Yay! It means how do you know mathematically? Um, well, I'm actually going to graph first because I think that then I can explain it in 2 different ways. So I'm going to look at the tortoise verse 0, 0, 1, 2, 2, 4. That goes off the charts, right? And then the hare is 0, 0, 1, 3, 1, 3. So you can already see which way this is going. Let me take a look at my rulers. It's much steeper, right? Look at the angle here. 71 degrees. And then we'll do good old tortoise. Faster isn't better, my friends, right? Can you imagine if you went to a really fast person to cut your hair? Doesn't mean it's going to be a quality haircut, right? You might have like some stripes down your head that you did not ask for. Okay, so blue is the tortoise and red is the hare. A couple of different things I notice here. If I'm going by just the mathematics of what I did with the tables and the constant proportionalities and the unit rates, I could just say the hare, and how did I know? Because the hare's unit rate is larger, right? You want more miles. If you're talking about speed, right? Faster is more miles per hour, as you know. Okay. Another thing that you can look at also, the line is steeper. Okay. What does that mean? It means that it is increasing at a larger, like a faster rate. Okay. Does that make sense? That is going to really be important later when we're covering slope. Just I'm like providing some foreshadowing. Spoiler alert. Okay? We're going to cover that when we hit slope. But basically, if you look at the steepness of the line, the hare's line is steeper because it's going more miles per hour, right? It's reaching a higher speed faster. Cool? All right. So those are the notes for today. You have a Desmos activity that I'm leaving for you in Google Classroom. It will not be due until next Friday. As such, if you have any questions for me in Flex or in math, you can ask me those questions on Tuesday because you will see me next on Tuesday of next week. So don't freak out if you look at the Desmos and you didn't get it or you watch this video and you're completely lost. I'm going to put extra videos in there for you to help out, but also I will be able to answer some questions for you on Tuesday concerning the material for today. See you then.